Hello everyone, I am back, and today we're talking about what integrals mean. And we're going to talk about how integrals are really just accumulators, and I want to make sure by the end of this video, this lesson, as you explore it, you have a better idea of what that means and you don't misinterpret it a certain way, because I've seen a lot of students misinterpret what these mean. So we're going to look at two examples and I'll talk about these examples. So we have an example here where v of t is going to be given to us, and it represents the velocity of a car in miles per hour. And it's represented by this function 3t squared plus 5t. Now say we wanted to find the integral of 1 to 3 of v of t dt. Now what's that mean? So what we should hopefully know is that this is the area under v of t from t equals 1 to t equals 3. And hopefully that's where you're at right now at the very minimum. I draw a graph out here. This is a parabola where one root is 0, so I think it's going to look something like this. Probably a little bit steeper, but it's okay for our purposes to understand this. And it's going from 1 to 3. We're finding the area under the curve of this graph here. Now, what's happening here now that we talk about context, though? So remember, v of t was in miles per hour, and we're talking about per as time changes in units of t, which is hours. So if we find the area under the curve here, well, that's going to be miles per hour times hours. And if you notice that hours goes to 1, so what we're left with is miles. So the area under the curve here is going to give us an amount of miles. Now let's get what the answer to this is. So if I plug this into my calculator, I go 1 to 3 of 3t squared plus 5t with respect to time. Let's see what we get. So we have math, integral 1 to 3 of 3x squared plus 5x with respect to x, and we get 46. That's nice. So what that 46 here means is that represents 46 miles. Notice the area, notice that the area is not always units squared. We're not talking about the amount of space that fills up a geometric shape. In context of this problem, the area under the curve is miles. Now what's this miles mean, though? It's important you recognize that it's not necessarily the miles traveled. What this is it represents the displacement. Or when I say not necessarily miles traveled, it's not necessarily the distance. Because remember that the antiderivative of velocity is not distance, it's displacement. So this is the displacement, which is the change in miles, is 46. So we're talking about something accumulating. That means that so if I go into more depth, from the first to the third hour, there was a change in 46 miles. So just understanding that it represents an amount. That's a change, just not necessarily, and it's a change that's accumulating, right? So maybe I can say it's a change that's accumulating. Now, I don't really like explaining it in the example of velocity and distance and time because I think it can get a bit confusing. So I made one more example that will help clear this up and show you a little thing here, okay? So it's not necessarily distance in that first one because it's really displacement. Now, in this example here, we talk about a function r of t that represents the rate at which math problems are completed per hour. And this function is given as negative 1/20th t squared plus 30. And what we know is that after 2 hours, I completed 70 problems. And the two things I want to solve here are how many problems did I complete from the second to fourth hour, and how many problems did I already have complete before I even started. Right? So if we're answering the first one here, 1, how many problems did I complete from the second to fourth hour? Well, this is a rate, so I know that if I take the integral from the second to the fourth hour of this function, this will give me the amount of problems completed from the second to fourth hour. Okay. And the way you can see that is if visually we have some function r of t, it's a negative quadratic here, where this is problems per hour, and we're talking about per hour. Well, notice when you do problems per hour times hours, what you're left with is the amount of problems. Okay. So if I put this in my calculator, what do I get? 2 to 4, the math integral from 2 to 4 of my function r of t, which is up here. So we have negative 1/20 x squared plus 30 with respect to x. And if I do this, we get 59.067 approximately. So that represents problems completed. Now, be very careful though. So this does, you might say, well, there's your answer, Ms. Shine. Is it though? This is the number of problems completed from t equals 2 to t equals 4. So how many problems I complete for my second, fourth hour? Careful what that's saying, because the change in problems that I did from the second, fourth hour, the amount that was added up was 59.067 problems. But you need to account for our starting position, right? This only tells us, how much something has changed. It does not tell you, where it started. And that is important to know, and that is a common mistake people always make with this. Is, okay, they say 59.067, I'm done. Well, kind of. You did 59.06 problems from the second to fourth hour, but the question is how many problems did I complete? Well, notice that at the second hour, I completed 70 problems. So if there's a function, say the antiderivative of r of t is problems completing p of t, well, that means that p of 2 was 70, which is our starting value. So we actually have to add 70 to this, in which the actual answer is approximately 129 problems were completed. You have to account for a starting position. Right? In this integral, what I could have done from the beginning is put 70 plus. I started with 70 problems, and I'm accumulating more or adding more from the second to fourth hour. Okay. And that's a big mistake that people end up doing on these integrals and understanding in terms of context. Now let's answer the second question here. So the second part of this question was, how many problems did I already have complete before I started? So then let's see, well, since we know the function r of t, which is the amount of problems I'm completing, the rate at which the amount of problems I'm completing, if I want to know from before I started, so I want to know how many problems I completed. So it's i.e., I want to know how many problems I completed from 0 to 2 hours, right? So we have the integral of, and now we're working backwards, so it'd be 2 to 0 of r of t dt. We want to know how many problems are completed from 2 to 0. But again, that's only going to tell us how many problems were completed from 0 to the second hour. If I want to know how many problems I completed, I have to subtract. I have to consider the 70 there too. And now this might confuse me when I say 70 plus 2 to 0. I myself, when I work through this, some students think this way. I don't know if you're one of them. I actually just jumped in my head to the second step where I started with 70 problems already completed, and I'm subtracting from 0 to 2. And that's what's happening here is from 2 to 0. If we work backwards, remember, if you switch the bounds, that area under the curve switches sign. So then that becomes negative. So we're going to know how many problems we did, 70 problems, and we're going to know how many problems we completed from the second to the second hour and subtract that off. And if I put this in my calculator, so 70 minus 0 to 2 of negative 1/20th t squared plus 30 with respect to t, what I'll get, let's put this in here, is 70 minus the integral from 0 to 2 of negative 1/20th x squared plus 30 with respect to x. And I get 10.133, in which at that point I can probably say about 10 problems were completed before the time started. And just to elaborate on that, if I took out the 70 minus, and just did the integral, well, notice from 0 to 2, it looks like I did roughly 60 problems. So this right here is I did roughly 60 problems from t equals 0 to t equals 2. I'll make sure I'm answering the question where it's how many problems did I get completed before I started? Well, I have to account for that starting value, that known value. And do note that when we do these integral functions, I don't know if you saw this, but if I look back at these two problems, this one was a rate function, and the first one, velocity, is a rate function, in which we can look at integrals of rates, because that'll give us an amount of something. What you usually wouldn't do is it wouldn't make sense to do an integral of a distance function d of t, dt, where d of t is distance. That doesn't really make sense, because what if you do the area under the curve, miles times hours equals miles hours? And I don't know what that is. So usually we look at integrals of rates, just something to connect this and hopefully help you understand that. So there it is. Integrals in context representing an amount of something accumulating, something adding up over time. But remember, when we talk about trying to find these problems, just don't forget, it tells you how much something is changing in that time period, but you have to know a fact about it. You have to know something about where it started to build off of that. Okay. Hope that makes sense to you, or you can figure out yourself. If you need anything, definitely let me know. Okay, bye-bye.